Let's talk about system design and how to deal with data contention. Basically, the question that we are looking at is what happens when multiple users modify the same data at the same time. For example, consider a ticket booking system. You have all these entities, event, uh, an event is being conducted at a venue, then the venue or the event has some seats, and then a ticket is purchased against a seat ID, event ID, and then we have a booking which is effectively a collection of ticket IDs. Consider this simplified workflow for ticket booking. The user selects an event, views the available seats, selects the seats, makes the payment, the seat is purchased, the database is updated, and the booking is confirmed. For the purpose of this particular discussion, let's assume that the seat reservation system is not implemented yet. So if and only if the seat reservation system has not been implemented, there is a chance that a seat is double booked. Now how that can happen is that there are two users A and B, both query for available seats and both see that okay, seat number 33 is available. Both complete the payment at the same time and then the database is updated. So this is how the flow of information might look like. You begin the transaction, you update the seat status as sold where seat ID is equal to 33. Then we check whether the updated row count is equal to 1. If not, then we roll back the transaction. Otherwise, we insert into tickets that okay, this user has purchased ticket for seat number 33, and then we commit the transaction. Now what might happen is that since both the users thought that seat 33 is available, transaction 1 for user A would create an entry against that particular seat for user A. Then transaction 2 for user B would also create an entry for user B, and then what that would mean is that both the users would have the same, will have a ticket for the same seat ID assigned to them. Now how do we deal with contention? So there are multiple ways to deal with contention. For single database nodes, we have two widely used mechanisms. The first is called pessimistic locks or row locks, which is a database level mechanism, and the second is called optimistic concurrency control. Then for multiple nodes or systems wherein there are multiple different services acting together, something like a microservice architecture, we have algorithmic techniques which include two-phase commits, saga pattern or other algorithmic techniques, and then we have the concept of distributed locks. So talking about optimistic concurrency control, you will use an additional identifier which will change on an update. So now if you know that this particular identifier will change on an update, now when you're updating, you check the database value against the known value. For example, you can add a version field to your seats table where effectively now first before beginning the transaction, you select the seat entry wherein you get the seat ID, status of the seat, and also the version of that database row where seat ID is equal to 33. So let's assume that this returned version 1 to you, right? So next update that would be there after a payment has gone through would be that you update the seats and you set status is equal to sold and the version you incremented by 1 where seat ID is equal to 33 and version equal to the old version number. So effectively, if your version number and the current version number in the table does not match, then 0 rows will be updated, in which case the whole transaction would be rolled back and the user would have to retry, right? Otherwise you insert your entry, otherwise your update goes through successfully and you insert an entry into your tickets table. Now while this is one way of doing things, you could also have an identifier which is something that changes in your database. Like for example, in this particular example, the seat status would change, right? So instead of checking against the version number, we could also have checked against the seat status. So we could set seat status is equal to sold where seat is 33 and status is equal to available. So in that way, we will also ensure that the user is not able to update this particular row if it has already been updated. Moving on, let's talk about pessimistic locking. What this means is that you just acquire database level, row level, or table level locks upfront. You fix all these race conditions, the contention conditions, by explicitly locking the rows. Or additionally, you could also make use of your database's transaction isolation levels. Or different databases have different set of isolation rules in terms of what data different transactions can see. Based on these database level primitives, you can create transactions which are atomic in nature, and you can ensure that your database remains consistent and you don't enter any contention issues. The pros of this approach is that it is very easy to implement, but this can have significant performance issues, specifically if you hold the row or table level lock for a long period of time. And also this particular approach has the chances of resulting in deadlocks, wherein one transaction is waiting on another table and that table is waiting on this transaction. So there could be deadlocks in the system, and then you'll have to figure out deadlock prevention strategies while you're designing this whole system for your particular needs. Moving on to the next topic, what if you were dealing with multiple databases or services? Like, what if the ticketing system was designed as a microservice, wherein you had an API gateway, then you had separate service for tickets, separate service for payments, and then these were acting independently, scaling independently, and storing data either to the same database or to different databases per service. For microservice or these sort of multi-node service architectures, we have two patterns which are very widely used. The first is called two-phase commits, which is a mechanism wherein you ensure that the transactions are strongly consistent in nature, and the other one is called a saga pattern, wherein you have eventual consistency, and these two operate differently. So we'll talk about the two-phased commits first. So with two-phased commits, we are effectively trying to create a distributed atomic transaction system, wherein we have one service, which is your coordinator service, and then it interfaces with all the participants in your system. So those participants could be service 1, which could be your ticketing service, service 2, which could be your payment service. The way two-phase commit system works is that you have a coordinator service, which interfaces with all the participant services in the system, and the coordinator will send signals to your participants and tell them to prepare for a particular use case. And once it receives acknowledgement signals from the participants, it decides whether all the acknowledgement signals are positive in nature or negative, or any of these are negative. And based on that, if all are positive, then it sends a commit signal to all your participants. Otherwise, it sends a rollback signal to the participants so that they can roll back whatever preparations they had done. The pros of a two-phase commit architecture is that you can maintain strict consistency in your solution. All the participants will either commit the data or roll back the data, so there is no inconsistency between the data that is being stored. But then you have certain disadvantages, wherein you now have one more component in your solution, the coordinator service or a transaction manager service, and this component can become a single point of failure or issues in your system. Moving on to the next pattern, which is the saga pattern. Now this pattern says that each service updates their database independently, and then all databases revert back to the original state if any of the step fails. Now this is an eventually consistent pattern, wherein what we try to do is that each service will first try to complete its work atomically. Let's say we had the same ticketing example. The ticket service could just block a particular seat. It says, okay, seat number 33 is reserved. Then it sends a signal to service 2 either via message bus or an event sourcing mechanism. And then service 2, based on the incoming message, it initiates some work, and then the results of that work is stored in its local database. Now, in case any of the transaction fails, there is a concept of compensating transactions, which are effectively reversal transactions, which are triggered if any changes had been done earlier in the chain. So just to illustrate, we had the ticket service. It will create a ticket order. Then we have a payment service which will process the payment. Then the signal goes back to ticket service, which updates the seat status, and then again the ticket service completes the ticket order. At each of these stages, if there is a failure, you have these compensating transactions listed in red. So if let's say the failure occurred at third point while updating the seat status, first order of action would be to revert the seat allocation. So this would be the first compensating transaction. Once this transaction is done, the event bus passes message on back to the payment service, which will then revert the payment with the compensating transaction, and then another message is generated which is consumed by the ticket service to cancel the order. Now this particular pattern can be implemented in two different ways. One is called choreographed saga pattern, wherein you use a message broker to pass messages along your services, or another pattern is called orchestrated pattern, wherein you use a centralized orchestration service to pass messages between these services. Now, since each of these service updates its database independently, this system will result in scenarios wherein your services report back status or update or data differently, but by the end of the reversal mechanism or end of the commit mechanism, all these services would be in sync. So this becomes an eventually consistent mechanism. Now, the last topic that I would like to talk about is distributed locks. So distributed locks try to solve the question, which is how do we reserve a shared resource? Like for example, in our ticketing system, again, if you were to reserve your seat, how would you do that? So one way to do it could be to add a lock status column or some multiple columns. One would be for the locking status, another might be for expiry date of that particular lock in your database. Now this implementing it like this is very easy, but there are challenges with respect to your lock revocation process, wherein you would require either additional services or you would have to set up some cron jobs to ensure that you revert the status of the database after the expiry time has elapsed. Now this mechanism is also susceptible to race conditions, wherein a user could be trying to extend the duration of the lock and the cleanup service is working at the same time trying to remove the lock. So you might, if you were to use lock status columns in your database, this is one particular scenario that you must be aware of. Another way to implement distributed locks is to use purpose-built solutions. Now, the most commonly used ones are Redis with some specialized locking implementation like Redlock, etc. Or you could also use Redis with TTL keys, TTL values set on your keys. Or you have different services like Apache, Zookeeper, or etcd, which are purpose-built to solve your distributed locking problem. Just to illustrate, if you were to use Redis to solve your ticket reservation problem, the way it would work is your API gateway, the user requests to select a seat. You hit your ticketing service. The ticketing service interacts with the database, get available seats. Then it would check against Redis to verify if a seat is reserved. If not, then the seat will be locked for X minutes. So this would be configured based on the application needs. In most systems, it's like 5 minutes or 10-minute hold on a seat. Now, it totally depends on your use case. And the lock is designed to be auto-released because you're using Redis, wherein you have TTL expiry time for your keys. So you set a TTL and then your lock is auto-released by Redis once the X minutes duration passes. Now next stage would be purchase. So the user attempts to purchase this particular ticket. So you hit the payment service, then you are going to interact with third-party payment gateways and all. So it might take a couple of minutes for your payment to go through. And once your payment goes through, so Mechanism number C would be you might have something like an internal message broker or an event bus running in your system, wherein you pass a message that okay, the payment has been updated. Based on that, now action number C would run, which could be a worker process which updates your seat status using your ticketing service and then confirms the ticket. Key takeaways, there are multiple approaches to handling contention scenarios. You will have to choose the best approach based on your system's functional, non-functional, performance, scaling, and consistency requirements. So you have to keep a lot of considerations in mind when you're designing how you solve contention for different scenarios in your system. Thank you. I hope you found these notes useful. If you want to download these notes, these are available at downloads.techwithpreet.com. Thank you. Enjoy your day.